In module 11.2, we're going to talk about our binary relational algebra operators of Cartesian product, our three set theory operators of union, intersection, and difference, join, and division. And we're going to talk about a number of different types of join when we get into that section. So a lot of interesting stuff there. We're going to start with the Cartesian product, which also sometimes you hear referred to as the cross product or just the product of two relations. And we already talked about the Cartesian product a little bit a couple of weeks ago when we were talking about the maximum cardinality of bringing together two relations, right? Because we talked about taking the cardinality of one relation, multiplying that with the cardinality of the other relation that's being joined to it, and that would be the maximum cardinality of the resulting relation. So we could kind of understand the computational complexity of joining those two relations together. So our relational algebra notation for the Cartesian product is just a big X like you would see in multiplication. So this is representing the Cartesian product of relation R1 and relation R2. And again, these are all binary operators, so they are all going to be having two relations interact with one another. So for all these upcoming examples, we are going to be using both the course relation and the department relation that we used in the previous examples, but we're simplifying them just a little bit in that we are only projecting a subset of the attributes from each one of the relations, and we're going to call course C and department D. And this is just to kind of save a little bit of space as we're going through these. So if we said relation C, our course relation, has 12 tuples, and relation D, our department relation, has 6 tuples, how many tuples will the Cartesian product of C times D have? So this is, again, this is like the maximum cardinality of the relation resulting from joining these two relations together, and we figure that out by just multiplying the cardinality of each one of these source relations together. So 6 times 12 is 72. So the result of the Cartesian product of relation C and relation D is going to have 72 fairly useless tuples for the most part. And this is a very truncated version of what the result would be. This is only the first 24 tuples, but what we see here are all 12 of the tuples from relation C joined to this first tuple from relation D, economics department in the Arts and Science College, followed by all 12 of these tuples from relation C joined together with the QAQM department in the business college. Okay, and then we would have another 12 tuples, which is the 12 courses combined up with the economics department in the education college. And then another 12 tuples of the 12 courses joined up with the mathematics department in the engineering college. Okay, so we wind up with a whole bunch of tuples that don't really mean a whole lot. Okay, so the Cartesian product by itself really isn't a super valuable thing, but what we can do is combine the Cartesian product with our select operation, and we can create something that is equivalent to a join operation, which is quite a bit more useful. And so we previously mentioned that our relational algebra operations or our relational algebra expressions can be nested within one another, okay? And that's exactly what we see here, is that we have this relational algebra expression, which is the Cartesian product of C times D, and that's going to result in this big messy relation with 72 tuples in it. But from that relation with 72 tuples, we only want to select the tuples where the value of D code in relation C is equal to the value of D code in relation D, representing the department that each course is offered by. Okay, so this whole expression, first you're going to evaluate the Cartesian product, and then you're going to evaluate this Boolean expression against this resulting relation. Okay, so whereas we originally had this big messy thing, only the tuples where this expression c.dcode equals d.dcode are going to be returned. Okay, so here, Intro to Economics, which has a value of 1 for c.dcode, and this department, Economics within the Arts and Science College, which has a value of 1 for decode, this tuple would be returned, while this one, where we have a value of c.dcode of 3 and d.dcode of 1, these tuples would not be returned. But Operations Research, which has a value of 3, and the QAQM department in the business school, which has a value of 3, this tuple would be returned. Okay, so this is going to be more useful because it's showing you the courses and the department that offers that course instead of just every possible combination.
Professor?
Yes?
Why did we do all this work with foreign keys if I don't understand why we are doing that.
So where this is going, so this expression here that we're evaluating, typically this is going to be representing your foreign key relationship. So it's all kind of going to be clicking together as we progress through this. Good thoughts, yeah. So okay, yeah, so this is what we just went through here, where we selected from the Cartesian product, or we did the Cartesian product, so this is evaluated, returns that relation, and then we select from this big messy relation only these, I think this winds up being 11 tuples where this condition of equality was satisfied, because I think we have, yeah, one of our 12 courses here which does not have a value for a department code. So this tuple is not going to be matched to any of these tuples in relation D because null is not equal to anything. But we're going to come back around to this kind of weird architectural history course that's hanging out here in a couple of minutes.
So can I ask, and you can mute me if needed,
but fine.
This is how we do the join, and is it that we did all that work with the foreign key because that would have given us an error if we're trying to enter data that doesn't fit into the domain, and that helps with normalization? Or do I just need to wait and be patient?
So we're really kind of talking at a slightly different level of abstraction right now with the relational algebra stuff. So I don't want to just tell you to wait, but I do think your question will be kind of satisfied shortly, if that makes sense. But yeah, I mean, when we're looking at this relationship between courses and departments, you're absolutely right in that this decode attribute in this course relation is a foreign key that is referring to this decode attribute in the department relation. Okay, and we're not really talking about it being a foreign key right now in this context, but that's absolutely what it is. So we'll be coming back around to that. But yeah, you're in the right mindset here. And so kind of carrying on through this and nesting more relational algebra operations together, right? So we had our Cartesian product, which we nested inside of this selection operation, okay? Here we have the Cartesian product, which is going to be evaluated, and from the resulting Cartesian product, we're going to select only the tuples where c.decode equals d.decode. So this is kind of like our foreign key relationship here that we're evaluating. And then further, we're only going to return tuples that evaluate true for this expression credit equals G. So we want only our graduate classes. And so this is going to be evaluated and result in another relation. And from that relation, we're going to project only these 4 attributes that we're interested in, and we would wind up with a relation that looks something like this. And so in the second half of class tonight, we're going to look at how we write a SQL query that would match up with this relational algebra expression. But moving on to our next binary relational algebra operations. So these 3 operations, which we've already talked about when we talked about set theory a little bit a couple of weeks ago: union, intersection, and difference. So as we've already mentioned, in order to use any of our set operators, the 2 relations must be union compatible, which means they have the same degree or the same number of attributes, and that the pairs of attributes from the 2 relations must be in the same domain. So even though it's called union compatibility, this is a requirement for union, intersection, and difference. So in this case, we have these 2 relations, relation R and relation S, and we can see that the degree for both of these relations is 6 because we have 6 attributes in each one. And comparing the pairs of attributes, we have section number, time, maximum students, room, course number, prof ID. These look like they are probably that the values of these attributes share the same domain, right? It wouldn't make very much sense to try to do set operations between 2 relations, even if they both had 6 attributes, but these 6 attributes were section, time, students, room, course ID, and prof ID, and the other relation was, first name, last name, weight, hair color, and height, right? It wouldn't make sense to do that because these aren't similar sets, okay? But in this case, the 2 relations are representing classes that are offered in the fall and classes that are in the Lindner building. So these 2 relations are union compatible. So if we were to look at the union of these 2 relations, this is essentially like OR, right? It's saying, are you in relation are you in relation R or relation S? And if you're in either one of these, then we're going to return that tuple in the resulting relation, okay? And one thing to point out here, so we had 5 tuples in relation R and 4 tuples in relation S. So kind of the first thing we might think is that the result of the union should have 9 tuples, right? Since you're getting all the tuples from both sides. However, note that we do have some overlap, right? We have this course that is offered in the fall in Lindner 108, this 902 AE 2013. So it's both in the fall and in Lindner, as is this course here. So the resulting relation actually has just 7 tuples because there is some overlap. And we can't represent these tuples twice in the relation. Well, one, because it's just not how sets work, but then also, of course, relations do not allow duplicates, so we can't have this same exact tuple twice in the resulting relation. Okay, so that's our union. Intersection is the equivalent of our AND operation, right? So this is asking for tuples that overlap, that are found in both relations. Okay, so this is sections that are offered in the fall and in the Lindner building, which are the same 2 tuples that we just identified as being overlapping between the 2 sets. And then our difference, and the relational algebra operator is this kind of upside down U for a intersection, and it's this kind of right side up U, except it's a little bit stretched out. It's not actually a U. This is a special Greek symbol here for a union. So upside down is for intersection. And then for difference, we just use a minus sign. And this can work in either direction. So if we say R minus S, this is asking for tuples that are in relation R, or that are offered in the fall, but not in relation S, right? So we're getting these 3 tuples here that are courses offered in the fall, but that are not in the Lindner building. And then if we ask it in the other direction, S minus R, sections that are offered in Lindner but not in the fall. And that would be these 2 courses here. So this is just kind of going back to the set theory discussion we had a couple of weeks ago. And then in the second half of class, we will be seeing how we can write SQL queries that reflect this relational algebra, which we'll also be doing in the SQL project in the coming weeks. And then maybe the most useful and kind of the most prevalent binary operation for interacting with data is the join operation. And there are a number of different types of joins we're going to be looking at, but basically the join operation combines related tuples from 2 relations into a single tuple in the resulting relation where the specified join condition is satisfied. So the actual relational algebra symbol for the join is this. It looks kind of like a bow tie or like an X with the ends closed up here, but do note that in your book it's printed as this, where we have an X enclosed in kind of square brackets. I'm not sure exactly why that is. My suspicion would be that when the book went to print, this special symbol here was not in the fonts that the book publisher was using to print or something like that. But you'll see it in the book as this, but this is the actual relational algebra symbol as we will be discussing it. So in order to join the 2 relations, they must be join compatible, which just means the join operation has to involve attributes that share the same domain. And then coming back to your question, Megan, this is what we describe in the foreign key constraint, where we have an attribute that shares the domain with the attribute to which it refers, right? Our foreign key, all values must be in the domain of values of the candidate key to which it refers. So that's what makes these relations join compatible. And so we write our join relational algebra statement by specifying one of our 2 relations, and then our join symbol, and then in a subscript here, the condition on which you are joining. And typically this is going to be that your foreign key is equal to the candidate key that it's referring to, and then the other relation. And also keep in mind that, of course, these relations or these representations of relations, R and S, are really relational algebra expressions that might be other relational algebra expressions in and of themselves that are going to evaluate down to a relation. Okay, so this might be more relational algebra expressions kind of nested in one another. So anyway, this is the general form of our join relational algebra, and the resulting relation from this join is going to have a degree or a number of attributes which is equal to the number of attributes in the first relation plus the number of attributes in the second relation. Okay, so if relation R has 5 attributes and relation S has 3 attributes, the resulting relation is going to have 8 attributes. And then the resulting relation will have a cardinality, or a number of tuples, equal to the number of combinations of tuples where the join condition is satisfied. Okay, so we don't really know ahead of time how many tuples are going to be present in the relation, in the resulting relation. We have to wait until we've evaluated every pair of tuples to really figure that out. So the big difference in the join and the Cartesian product is that the Cartesian product gave us every single combination of tuples, whereas our join is only going to give us combinations of tuples where the join condition is satisfied. Okay? So kind of the interesting thing about this is we saw how we could make the Cartesian product a little bit more useful by nesting our Cartesian product inside a select operation, which evaluates the values of two attributes for equality, right? So this Cartesian product and selection is going to result in the same relation as this join expression here, where we're joining relations C and D based on this criteria, okay? And the way we would write the sequel to go along with these relational algebra expressions is actually a little bit different, whether we're going to create the Cartesian product and then select a subset of tuples from that versus just doing a join. Now, modern DBMSs, when they evaluate your sequel, I don't think you will normally see any performance difference whether you take this approach or this approach, because they kind of figure that out and keep you from shooting yourself in the foot. But you will write the sequel differently, and we'll look at how the sequel differs when we start writing that in the second half of class. Or actually, I think we won't be getting to this these binary sequel queries until next week, but we'll be looking at that.
Professor?
Yes.
On the last slide for cardinality, I know we add those now since we're joining them, but do you count decode twice in that for your cardinality? Like, would your cardinality be 7 or 6 here?
So you're asking about the degree, the number of attributes, and yeah, that's a good question. And in fact, it would be 7. Okay, because that joining attribute is going to be repeated, and that's kind of superfluous, useless repetition. And we're going to be talking about that in just a minute. So almost like you're precognizant and looking into the future here.
Thanks.
Good thoughts. So we'll come back to that in just a moment. But before we get there, I would point out that we can, of course, further refine our relational algebra expression, and we could project only certain attributes we're interested in, thereby reducing the degree of the resulting relation. Okay, so in this case, we have this join expression where we're joining relation C with relation D based on this expression of equality. So this is going to be evaluated and return a new relation. Okay, from that relation, we're going to select only tuples where the value of credit is equal to G. And that's going to create a new relation. And from that relation, we are going to project only these attributes, C.name, credit, D.name, and college. So this is the name of the course, C.name, and D.name is the name of the department. A little bit confusing because these attributes have the same name inside those relations, okay? But we mentioned that whenever we refer to an attribute, we can prepend the name of the relation or the name of the table, which makes it globally unique within your database, okay? So these 3 nested relational algebra expressions would evaluate to return this relation here, right? So we joined relations C and D based on this statement of equality, C.decode equals D.decode. Then from that, we selected only tuples where credit equals G. So we see that panning out here. and then we're projecting only these 4 attributes we're interested in. So there are, as I mentioned, a number of different types of joins, and what we've been talking about so far, kind of the default or the base join, is the equijoin, where we're joining 2 relations together based on some condition of equality. The natural join is just kind of a special case of the equijoin, and the relational algebra symbol for that is the asterisk, and this actually addresses the issue that you just brought up, Santiago, about the repeated joining attribute. So the natural join will get rid of that extra repetition. So we'll look at that in just a moment. The theta join, kind of a weird duck and not something we see used very often, but we bring together tuples based not on a condition of equality, but on a condition of inequality. Okay, so we want tuples where the foreign key is not equal to the candidate key to which it refers, basically. And then we have 3 types of outer joins, the left outer join, right outer join, and full outer join, which will allow us to bring back tuples from one relationship or the other relationship or both relationships, even if they don't have a matching tuple in the other relationship. Okay, and we'll give some examples of how that works here in just a moment. So yeah, as I mentioned, equijoin, this is a join condition on the condition of equality. And yeah, as was just pointed out, when we bring these 2 relations together, relation C having a degree of 4 and relation D having a degree of 3, we wind up with a resulting relation with a degree of 7, but the value of C.D code is always equal to the value of D.D code, right? It has to be, because that's the condition on which we joined the 2 relations. But this isn't telling us anything new, because it's always going to be exactly the same as the other value of D code. So that's what the natural join addresses. It just omits this the second attribute that you were doing your joining on. So if we performed this natural join, so just notice we changed the symbol from that little bow tie looking thing to an asterisk here, it is going to reduce the degree of the resulting relationship by 1 because we're not repeating this attribute. So the tricky thing about a natural join, and the reason that I'm not really a very big fan of the natural join, is that in order to do this, the attribute in both, the joining attribute in both of the relations has to have the same name. And that just seems to me like kind of an arbitrary limitation on how you're going to name your attributes in your database. So I don't know, I hate depending on these attributes that I want to do the join on having the same name, which is the requirement of the natural join. So another thing that we could do is to just do a regular equijoin and then just project only the attributes that we are interested in, and don't project this the joining attribute from both relations, right? So we're going to get C.name, course credit, and C.D code, so the 4 attributes from relation C, and then project D.name and college, but don't project D.D code, okay? And so this is going to have the exact same output, the exact same resulting relation as doing a natural join. And similarly, we could do the Cartesian product and select from the Cartesian product on this condition of equality, and then project from that relation these 6 attributes that we're interested in. Okay, so these are 3 different relational algebra expressions, and we would write this SQL in 3 different ways to match these relational algebra expressions that are going to have the exact same output. And that's one thing that we're going to find over and over again as we get more into writing SQL. And this is something that I ask you guys to do in the SQL project assignment, is I ask the same question for some of these 2 or 3 times, but specify, write this using an inner join, or write this using a subquery, or write this using a set theory operator, right? Because there's going to be multiple ways almost all the time to write a SQL query to get the same results. And sometimes what you pick is just going to be a matter of kind of your preference and which one you like working with more. But then sometimes it's going to be much easier to write a query using one approach than another, or you're going to get better performance using one approach as opposed to another approach. So I want you guys to be familiar with a couple of different ways of getting to the same result, and that's what we see here. Now the theta join, as I mentioned, kind of a weird situation here. So in this case, the symbol looks the same as our Equijoine, except for our joining condition. Instead of saying c.decode equals d.decode, we use this symbol here, which means not equal to. Okay, and this is just a less than sign and a greater than sign kind of mushed together. Okay, and so now we're going to create a relation that has tuples where c.decode is not equal to d.decode. Okay, so this is basically going to tell us, here's all of our every tuple from our course relation matched up with every tuple in our department relation, but it's every department that doesn't offer this course, which is kind of a weird thing to be asking for, right? So whereas when we had that Cartesian product, we had these 72 tuples, and we said only 12 of them or 11 of them were really very meaningful because they represented the department that offers a course. The theta join is taking that Cartesian product and then getting rid of all of the tuples that I previously called like the meaningful ones or the useful ones, right? And only keeping the ones that I don't see as being super useful. So there's not a ton of applications for a theta join. You might find yourself in a situation where you want to like create a report of all of the classes a student has not taken, right? Or all of the students that have not taken a class, right? Or maybe if you've got, some employees in different buildings that they may or may not have access to, and you want to create a report of all buildings that certain employees don't have access to or something like that, a theta join might come in handy, but it's one of those things that's kind of an infrequently used approach. And then our final set of joins we're going to be talking about are the outer joins. And these actually do get used quite a bit more. So when we have an inner join, if we have any tuples in one relation or the other that don't match up with a tuple in the relation that it's being joined with, those tuples are not returned at all. And additionally, any tuples that have a null value for the joining attribute are not going to be returned because as we're going to discuss, I'm pretty sure this comes up in the second half of class, when we try to evaluate a value of null for equality, null is never going to be equal to anything. It's not going to be equal to null because null isn't a value that exists. It's not something that we can make any kind of expression of equality or inequality to. So I mentioned earlier in the semester that we generally want to try to avoid having null values in our database as much as we can because they're just difficult to work with and they cause problems. And we're going to start now seeing some of the problems that null values will create. So these outer joins, our left, right, and full outer joins, are going to allow us to keep all of the tuples in one relation or the other, or both, even if they don't have a matching tuple in the other relation. So our left outer join is our little bow tie symbol, except that it has these two little arms on the left side of the symbol, or in your book, they illustrate it like this. And this is going to keep every tuple in the relation that is specified literally on the left side of this symbol. Okay, so this is a left outer join. It's going to return every tuple from relation R, even if it does not have a matching tuple in relation S. And it's also going to return every tuple that is matching or that has a similar value of the attribute that we're joining on between these two relations R and S. And so it's going to give every tuple from R, and then for the values of the attributes from S, it's just going to kind of pad that out with null values. The right outer join, unsurprisingly, looks a lot like the left outer join, except the R's, or the little arms, are on the right side of the symbol. And that is going to keep every tuple in the second relation, or the relation that's specified on the right side of this symbol, even if it doesn't have a matching tuple in the other relation. And then the full outer join, which just has the little arms on both sides, is going to keep all tuples from both the relation specified on the left and the relation specified on the right, as well as all the tuples that do meet the joining condition of equality. So recall that I pointed out earlier that we have this one course here, Architectural History, which kind of strangely does not have a value for department code. And so when we did an inner join, we wound up with only 11 tuples in the resulting relation because architectural history, this value of null for D code, was not equal to any of the values of D code in our department relation. And similarly, see, we have courses for Department 1, for Department 3, 4, 6, and 7. However, we don't have any courses in the philosophy department that has a value of 9 for D code. Okay, so if we do a left outer join of D and C on this condition of D.decode equals C.decode, the resulting relation is going to have the 11 tuples where D.decode is equal to C.decode, but also any tuples from relation D, even if they don't have a matching tuple in relation C. So we get this philosophy department returned, and then we just have values of null for name, course number, credit, and D code. Okay, so we get all of the tuples from D, even if they don't have a matching tuple in C. Now our right outer join, kind of the same thing, except this time we're going to get every tuple from C, even if they don't have a matching tuple in D. Okay, so this is going to return this weird architectural history course that does not have a department. And then finally, if we do a full outer join, we're going to get everything from D, even if it doesn't have a matching tuple in C, and everything from C, even if it doesn't have a matching tuple in D. So we get our philosophy department that doesn't have any courses, and we get our architectural history course that doesn't have a department. Okay, so when we did our Equijoine, the resulting relation had these first 11 tuples. When we did our left outer join, we got our 12 tuples, including the philosophy department. And when we did the right outer join, we got 12 tuples that included the architectural history course. And when we do the full outer join, we get this relation with 13 tuples containing both the philosophy department and this architectural history course. And one thing I'll point out here about the right and left outer join, if you just switch the order that you specify these relations in, D right outer join C is the exact same thing as C left outer join D, right? It really doesn't matter which way you specify them. They're the exact same thing, just in reverse. And when we write this in SQL code, as we will see next week, we do have to be careful because we're going to type out the words left outer join and right outer join, and the side of left outer join or right outer join that you specified the names of the tables on is going to determine which table gets all of the tuples brought back and which one does not. And then our final binary operator that we're going to be talking about is the divide operation. And this, I think I may actually see this used less often than the theta join. It's an interesting situation here where we are looking for the set of tuples in one relation that matches all tuples in another relation. Okay, so in this case, we have this relation R, which lists all of the terms that a bunch of courses are offered in. And then this relation S, where we've specified a number of different terms that we're interested in. And when we divide relation R by relation S, the resulting relation is going to contain all of the tuples from relation R where this attribute term matches all of the attribute term from the other relation. Okay, so we're not going to get any of these tuples where say a course is only offered in fall and spring of 2016 because we're looking for only tuples where the course is offered in fall, spring, and summer of 2016. So we get these two courses, MIS 3360 and MIS 4374, in the resulting relation. Now, one thing to note here is these relations that we're looking at here, relation R and relation S, most likely these are not tables that are stored in the database. These are probably the result of some other relational algebra expression being evaluated to get down to just this small number of tuples in this single attribute